The topic for today is Myhill-Nerode Theorem. And before we discuss Myhill-Nerode Theorem, we need to set some background. Let us start with refinement between relations. Consider the binary relations R1 and R2 defined on the set A, which is just 1, 2, 3, 4. And the relations are defined as R1 is this set of pairs and R2 is this set of pairs. You can see that R1 is defined as follows. A pair AB is related under the relation R1 if and only if A is less than B. You can see that from the set A, all such pairs are included, and precisely all those pairs are included in R1. And what will be R2? How is it defined? Not difficult to see. This is the definition. A pair AB is related under R2 if and only if B is equal to 2A. So that is how these relations are defined. Now an interesting question is there a relationship between R1 and R2? Can you see any relationship between R1 and R2? You can see that each pair of element in R2 is contained in R1. 1, 2 is here and 2, 4 is there. So R2 is completely contained in R1. Mathematically, you can say that for all A and B, if A and B are related under R2, then A and B are related under R1. So, a relation in R2 implies the same relation in R1. Or you can equivalently say R2 as a set of pairs is a subset of R1. So, this is exactly the case. These two are equivalent mathematical statements defining their relationship. Here it tells that whenever A is related to B under R2, then A must be related to B under R1. Equivalently, this can be represented as the relation R2 as a set of pairs is a subset of R1. And then you can say that R2 is a refinement of R1. That is, when R2 refines R1, that means R2 is completely contained in R1 as a set of pairs. Or whenever two elements are related under R2, the same two elements must be related under R1. If R2 and R1 satisfies this property, then R2 is said to refine R1. We can consider one more example before we formalize the definition of refinement between relations. So consider the binary relations R1 and R2 on N0. N0 means natural numbers with 0, defined as what is R1. A and B are related under R1 if and only if A modulo 2 is equal to B modulo 2. That is, when you divide both A and B with 2, you will get the same remainder. That is R1. And R2 is defined as A and B are related if and only if when you divide A and B with 4, you will get the same remainder. So that is the definition of the relation. I hope it's clear. And it's not difficult to verify that R1 and R2 are equivalence relations. For the interest of time, I'm not going to see the proof for that. You can do it offline, but it is easy. So R1 and R2 both are equivalence relation. Please verify offline. And because R1 is an equivalence relation, you know that R1 will partition N0 into a number of disjoint partitions called equivalence classes. And these are the equivalence classes induced by R1. That is, all these elements are even numbers, and these numbers are those numbers which will give the remainder as 0 when you divide it with 2. You can see that any two even numbers are related, because if you divide an even number with 2, you will get 0 as remainder. Similarly, here the set of all odd numbers, if you divide any odd number with 2 you will get 1 as remainder. So any two odd numbers are related under relation R2. Sorry, under the relation R1. And I have selected the least number as the representative element of this equivalence classes. And pictorially, using a Venn diagram, you can represent N0 is the set of all natural numbers with 0. It is partitioned into two sets. The equivalence class for 0, which is the set of all even numbers, and the equivalence class for 1, which is the set of odd numbers. Now, look at R2. R2 is again an equivalence relation. Now, I hope you know the equivalence classes induced by R2, which are these. Because now it is modulo 4. So, the remainders 0, 1, 2 and 3 will form separate equivalence classes. These are all the elements. When you divide it with 4, you will get 0 as remainder. Here 1 as remainder, 2 as remainder and 3 as remainder. And now can you see any relationship between R2 and R1 here also? So here you can see that if you carefully look at the equivalence classes, you can see that the equivalence class for 0 in R1 is subdivided into equivalence classes 0 and 2 in R2. So the set of all even numbers is divided into two separate equivalence classes in R2. This is those which will give you 0 when divided by 4, and this is all these things that will give you 2 as remainder when you divide it by 4. So actually the equivalence class 0 is subdivided into two equivalence classes in R2. Similarly, you can see that the equivalence class for 1 in R1, that is a set of all odd numbers, is subdivided into two equivalence classes in R2. And pictorially, you can say that this is the set of all equivalence classes. And comparably, this equivalence class of R1 is subdivided into two equivalence classes in R2. And this equivalence class, that is the even numbers in R1, is subdivided into two equivalence classes in R2. And here also you can see that whenever two elements are related, either they are in when they are in any one of these equivalence classes. You can see that from class 0, if any two elements are related, then they are related under this class. And for 2 also, if these two are related, both are even numbers, so it comes to the equivalence class for 0. So whenever you can see that whenever two elements are related under R2, these are also related under R1. So here again R2 refines R1. But if R2 and R1 are equivalence relations, then when R2 refines R1, you have a nice property. The equivalence classes of R2 are partitions of the equivalence classes of R1. So here you can see that these equivalence classes are partitions of this equivalence class in R1. So this is subdivided into 2. Similarly, this is subdivided into two equivalence classes. And this is a very important property that we need to prove Myhill-Nerode theorem. So the only thing that you may have to remember is when there is a refinement relation between equivalence relations such that R2 refines R1, then the equivalence classes of R2 is contained in equivalence classes of R1, or in other words, equivalence classes of R2 are subdivisions or partitions of the equivalence classes of R1. That means whenever R2 refines R1, the number of equivalence classes induced by R2 will be more than the number of equivalence classes defined by R1 whenever R2 is not equal to R1 or not identical to R1. When R2 and R1 are two equivalence relations such that R2 refines R1, then there will be more number of equivalence classes induced by R2. This is a very critical point that we need to use in the proof for Myhill-Nerode theorem. So if R2 refines R1, then the number of equivalence classes induced by R2 will be more than the number of equivalence classes in R1. And now it's the time for us to formally define the refinement between relations, and we can define it as a binary relation R2 on a set A is said to refine another binary relation R1 on the same set if for all pairs of elements xy in A cross A, if x and y are related under R2, then they must be related under R1. If R2 and R1 satisfy this property, then you can say that R2 refines R1. So that is the definition of refinement between relations. And recall that if R2 and R1 are equivalence relations and R2 refines R1, then the number of equivalence classes induced by R2 will be more than the number of equivalence classes induced by R1. So now just recollect Myhill-Nerode relation that we discussed in the last class. We saw that a binary relation for a language L over an alphabet set sigma is said to be an MN relation if it satisfies four properties. That is, it's an equivalence relation, it's the right congruence, it refines the language, and it is of finite index. Hope you remember this from the previous lecture, otherwise please do it again. Now, the relationship between Myhill-Nerode relations and DFAs. In the last class, we have seen algorithms for generating a DFA from an MN relations and also an algorithm for generating MN relations from a DFA. So this is what we discussed. If you start with a deterministic finite state automata, you know that there exists a construction or algorithm from DFA to MN relation, which will give you an MN relation. And there exists another construction which will take an MN relation as input and gives you a DFA. And in the last class, we saw that these two DFAs are isomorphic. So effectively, it tells us that these two constructions are inverse up to isomorphism of DFAs. So here we started with a DFA and ended with a DFA. They are isomorphic. Or you can start with a Myhill-Nerode relation. Suppose you have a Myhill-Nerode relation, then you can apply this construction first to get a DFA. Then from this DFA, you can apply this construction to get a Myhill-Nerode relation. And in this case, we saw that these two Myhill-Nerode relations are identical. So this is what we saw, and this is the relationship between MN relations and DFA. So what it tells us is that there exists a one-to-one correspondence between DFAs and MN relations. For every DFA, there exists an MN relation, and for every MN relation, there exists a DFA. Okay, now is the time for setting the basis for Myhill-Nerode theorem. First, we are going to discuss a canonical equivalence relation on the strings of an alphabet set. Consider this relation. Let L be a language. L can be regular or non-regular or an alphabet set sigma. Now, consider the equivalence relation on sigma star defined as this. X and Y are related under this canonical equivalence relation. Let me call it as the canonical equivalence relation for L. Okay. If and only if for all strings Z, if you append the string Z to both X and Y, XZ is in the language if and only if Y is in the language. That means under the canonical relation, if X and Y are related, then if you append the same string Z to both X and Y, the resulting strings XZ and YZ are in the language, or both XZ and YZ are not in the language. That is, whenever they are related, and then if you append the same string to x and y, the resulting strings, that is xz and yz, either they are both in the language or they are both not in the language. So this is the definition of the canonical relation. And now see which are the properties satisfied by this relation. This is the relation. The first property is that it's an equivalence relation. So why is it? Because it is reflexive. We can prove it. Because for all strings z, we can say that xz is in the language if and only if xz in the language. Actually, this is a very straightforward case. If xz is in the language, then xz is in the language. If xz is not in the language, then xz is not in the language. Then by this definition, you can say that x is related to x. So it is reflexive. Second, it is symmetric. Why is it so? Assume that x is related to y. Then by this definition, you can say that for all z, xz is in the language if and only if yz is in the language. Then only x and y are related. Now you can rewrite this as for all z string z, yz is in the language if and only if xz is in the language. I am just changing the order in which I am writing this. This equivalence is a symmetric relation. That's why. And semantically you can see that this is okay. And if this is the case, then by this definition you can say that y is related to x. So whenever x is related to y, y is related to x, and hence it is symmetric. Third property is transitive. Why is it so? Assume that x is related to y and y is related to z. So here we have three different strings x, y and z. So in order to take this string, we need to consider another string. I am going to consider it as w. Then for all w in sigma star, because x and y are related, you can say that xw is in the language if and only if yw is in the language. And we are also given that y and z are related. That means for all w, yw is in the language if and only if zw is in the language. So these two tells us that for all w, xw is in the language if and only if zw is in the language. So from this definition tells us that x and z are related. So we proved that whenever x is related to y and y is related to z, x is related to z, and hence the relation is transitive. So we established that the canonical the canonical relation is an equivalence relation. Second, it's a right congruence. So right congruence means whenever x is related to y, then for all inputs impulse a, xa is related to ya. So it is a right congruence. Maybe we can prove that using the method of contradiction. For the purpose of contradiction, we need to prove that xa is related to ya whenever x is related to y. For the purpose of contradiction, assume that there exists a such that xa is not related to ya under the relation. Why is it so? By this definition, then we know that there exists an z for which this is not correct. So you can write it as there exists a string z such that xa is in the language and ya is not in the language. You can write it in the other way also, but without loss of generality, I can say that xa is in the language and ya is not in the language. Because there exists such an z, then xa cannot be equivalent to ya. And if this is the case, I can say that there exists a w such that xw is in the language and yw is not in the language. There exists a string w for which xw in the language and yw is not in the language. Why? Because you can substitute w as a z. Then I am exactly telling this w as a z. Then these two are equivalent. Okay, now from this, using the definition of the relation, we conclude that x and y cannot be related. That is, whenever xa is not equivalent to ya, then x cannot be equivalent to y. So, we got a contradiction, and hence, whenever x is related to y, XA is related to YA. So it's right congruence. Then third property, the canonical relation refines the language. That means if X and Y are related, then either both X and Y are in the language or both X and Y are not in the language. How will you prove it? Assume that X is related to Y. Then by definition you can say for all Z, XZ is in the language if and only if YZ is in the language. Then you can say X is in the language if and only if Y is in the language. How can you say this? You substitute Z as epsilon. If you substitute Z as epsilon, it is a string. You will get exactly this. X is in the language if and only if Y is in the language. That is X related to Y. Then X is either X and Y are in the language or X and Y are not in the language. Hence proved. Thus, the canonical relation satisfies all properties of an MN relation except the finite index property. The only other property that a Myhill-Nerode relation is satisfying is that it is having finitely many equivalence classes. That is the only thing that this may not satisfy. We don't have any proof for that. In general, that is not true also. So this is a canonical equivalence relation. Later we will see why is it canonical. Okay. Now canonical equivalence relation on the string set and Myhill-Nerode relations. This is we can have a very beautiful theorem, and the theorem is this. Let L be a language over sigma. L be a language, and this be an arbitrary Myhill-Nerode relation for L. So we are given with a language L and an arbitrary MN relation for L. And from the previous lecture, we know that for any regular language, there exists a MN relation. So that means if there exists an MN relation for L, it is regular. Yeah. So what is given is an MN relation for a language. And now you look at our canonical equivalence relation. Then the theorem is very strong. It says that then the arbitrary Myhill-Nerode relation must refine the canonical relation. This is the relation that we defined in the previous slide. So we are claiming that an arbitrary MN relation for the language, that is this one, refines the canonical relation. If this is the case, then we can say that that is why it is said to be a canonical equivalence relation, because any Myhill-Nerode relation for a language must refine the canonical relation. Maybe we can prove it, and here is how you can prove. Suppose X and Y are related by the MN relation. So an arbitrary relation is given, that is this one. Suppose X and Y are related. Then you can say that for all Z, XZ is equivalent to YZ. Why? Is because you know that an MN relation is right congruence. Okay, then you using induction on the length of Z, you can prove that XZ is related to YZ. Because you know that whenever X is related to Y, XA is related to YA. Then you can prove that XAB is related to YAB. Similarly, it goes, and it is easy to prove that XZ is related to YZ. If that is the case, then we can say that for all Z in sigma star, XZ is in the language if and only if YZ is in the language. Why is it so? Because this relation refines the language. If it refines the language, whenever two strings are related, we know that either both are in the language or both are not in the language. This is exactly what we are saying here. And from this, we know that now X is related to Y under the canonical relation, because it follows from the definition of the canonical relation. This is the definition of the canonical relation. So what we proved is that whenever X and Y are related by an arbitrary Myhill-Nerode relation, then it must be related by the canonical relation. Now if you recall the definition of refinement, you know that this refines this. That is, whenever two elements are related by this relation, then the same two elements are related by this relation. Okay. So this is a very important theorem. And there are some nice corollaries. The first corollary of this theorem is that the construction that we discuss to construct a deterministic finite state automaton that from the Mn relation, and if you apply that on this canonical relation, produces the minimal state deterministic automata for any language over L. Now there may be a confusion because we know that when compared to an Mn relation, the canonical relation may not satisfy the finite index property. In that case, you will get an automata, deterministic automata, which is having infinitely many states. That is the only case. And that is why I said deterministic automata, not deterministic finite state automata. So, it's because we know that the equivalence classes of an equivalence relation R2 are partitions of the equivalence classes of R1 whenever R2 refines R1. This is what we saw in the beginning of this lecture. Here we know that the Mn relation refines the canonical relation. So which will contain more number of equivalence classes? The Mn relation, because the classes of the Mn relation are going to be partitions of the classes of this relation. That is what we learned in the beginning of this lecture. That means this relation will give you more number of equivalence classes, and this will give you less number of equivalence classes. That means if you apply the automata construction on the canonical relation, then the resulting automata will be the one with the minimum number of states. So very nice result coming from this theorem. Another corollary, and which is also very nice, saying that the canonical relation is an Mn relation when L is regular. It's very important. If the given language is regular, then the canonical relation is an Mn relation. Mn relation means it also satisfies the finite index property. And why is it so? It's a corollary of this theorem, because you know that if there exists a regular, if the language is regular, you know that there exists an Mn relation. Mn relation means finitely many equivalence classes. Then from this theorem we know that that relation refines the canonical relation. That means the number of equivalence classes here is finite because you have more number of equivalence classes in this relation, and because it is regular and Mn relation, we know that here there are only finitely many equivalence relations. If it is K, it is guaranteed that the number of equivalence classes here will be less than or equal to K, which follows from the refinement relation between these two relations. Okay. And now it's a time for us to state and prove the theorem Myhill-Nerode. And this is the theorem. Let L be a language over sigma. L is a given language over sigma. Then the theorem Myhill-Nerode tells the following. The following three statements are equivalent. What are the statements? L is regular. Second, there exists an Mn relation for L. Third one, the canonical relation is of finite index. That means this is an Mn relation. So, if Myhill-Nerode theorem tells us that these three are equivalent, meaning if there is L is a regular language, then there exists an Mn relation. And if there exists an Mn relation, then the canonical relation is of finite index. And if the canonical index Myhill-Nerode relation is of, the canonical relation is of finite index, it's a Myhill-Nerode relation, and hence we know that this is a regular language. Maybe we can try to prove it. It is easy now. You can say that 1 implies 2 because L is regular means there exists a deterministic finite state automaton for L without loss of generality. Then you can apply this construction to obtain a Myhill-Nerode relation because you have a DFA, and hence you can obtain 2 from 1. Now you can see that 2 implies 3. Why is it so? It's because you know that you have a Myhill-Nerode relation for here, and from the previous theorem we know that any Myhill-Nerode relation refines the canonical relation. And because the Myhill-Nerode relation contains only finitely many equivalence classes, this refinement tells you that the number of equivalence classes here is less than this, and hence it is of finite index. And finally, you can see that 3 implies 1 because you can use this construction. If you apply the construction on the equivalence, on the canonical relation that is now a Myhill-Nerode relation, it produces a DFA because now it has only finitely many equivalence classes. And this is theorem Myhill-Nerode. And we have proved it. And there are a number of applications of Myhill-Nerode theorem that we will discuss in the next class. So today we have stated and proved Myhill-Nerode theorem. Thank you.